Thank you very much for coming back after morning tea. It is appreciated. We've got another full session of talks. First cab off the rank is Dr. Janelle Simpson, Director, Minerals Geoscience at GSQ, and Janelle will be speaking about GSQ's collaborative partnerships. Welcome, Janelle.
I have been warned that I'm probably too short to read the words here, so I brought my own words as well. Unfortunate disadvantage of being so short. All right, so good morning, everyone, and welcome back from morning tea. I wanted to start my talk today by acknowledging the traditional owners of the land on which we're gathered today and pay my respects to elders past and present. And I want to ask that we just take a moment to reflect on what our responsibilities are as we walk towards a path to treaty in Queensland. So today I'm going to take you through how we think about collaboration in the GSQ, highlight some of the outstanding projects that we have going on in this space. I think it's important to communicate why we're choosing to work on particular things, such as circular economy and mining, in addition to our more traditional pre-competitive geoscience initiatives. So if I start with a snapshot of, they're not there, of the funding packages that make our work possible. These have already been mentioned this morning, but we have two primary work programs that we're working on inside the GSQ at the moment, and that's the New Economy and Minerals Initiative and the Queensland Resources Industry Development Plan. Over the rest of the day, you'll see a wonderful array of projects being conducted by the GSQ staff under these funding packages. All of our projects are aimed at how we help explorers find critical minerals that we need as a society. These projects range from regional geophysics through various scales of geological mapping to microscopic characterisation of our known deposits in Queensland. Collaboration has always been a really key part of our geoscience-focused programs, and in recent years, we've seen an expansion of the scope of our projects and how our limited life funds are being used on collaborative projects across the mining value chain. Today, I will showcase some of the incredible work being done in that space with our collaborators across Australia and the world. So why have we seen this change? What's going on? Why is the GSQ up here talking about circular economy instead of just geoscience? Why are we being involved in a broader range of projects? The future is shaping up to be different. We are seeing an increased interest, particularly from investors, in the role of ESG and the circular economy as we move towards our society's commitment to net zero. In industry, we're already seeing increased collaboration and coordination across the mining value chain to a future where people want to be able to track their responsibly produced minerals. We are seeing a move towards increased transparency and social responsibility, and this pace of change is quickening not only in the ESG and circular economy space, but also in the demand for minerals that we're seeing in Queensland. Our job at the GSQ is to ensure the future security and performance of the resources sector in Queensland and to lay the foundation for exploration success. So the question becomes, if the landscape that exploration happens in is changing, how can we facilitate the industry of today the way we always have, and how can we enable the mining industry of the future? You might notice that I have shamelessly stolen this from Rick Valenta this morning, but I think it's a useful framework for understanding how things are changing for the GSQ. Traditionally, we've had a strong focus on the upstream part of the mining value chain, highlighted here in orange, generating data and knowledge that feeds into industry exploration, as well as directly funding innovative exploration by companies through our collaborative exploration initiative. As the government and industry focus has shifted across to critical minerals in their production, we've seen a broadening of focus for the work supported under GSQ packages. This ties to an acknowledgement that for many of the minerals currently being considered critical, more than support at pre-competitive data stage is required for their successful production. We need support across the value chain to really get these projects into the pipeline. So over the last 3 years, we've seen an expansion of projects from just the pre-competitive stage across this entire value chain. We need innovation across all of these areas to produce the staggering amount of minerals that we're going to need to accomplish net zero. Our collaborative projects rely on bringing together minds from research organisations, industry and government together to tackle some of these really complex multi-part research projects. The strength of our research institutes in Australia is a key competitive advantage that we have as a resources sector. And the projects that we're running at GSQ is trying to focus that competitive advantage on the problems that we think are the most important at the moment. We've also not just been working in the research space and data generation space, but we've also been broadening our relationships with other communities. So we've been working with JOGMEC in Japan, as Tony mentioned, but also working with Korean organisations and building ties with Europe and American groups. All of this is in an effort to ensure that once we find a critical mineral deposit, we have the processing and market already worked out to bring these commodities into production and sale as quickly as possible. You've already heard this morning there's a shift in government focus to investing in onshoring more of the production value chain for some commodities. And so what we're trying to do is generate collaborative projects that are supporting the industry across the value, across that life cycle. So this is not everyone we work with. None of the research we do is done in isolation. Even the projects that look like they're internal GSQ projects have some element of collaboration to them. This is not exhausted. There are many here that can't be shown simply because I ran out of room and time to put extra people on here, unfortunately. But we couldn't do what we do without the involvement of industry, the feedback we get from industry, and the involvement of researchers across various organisations. Collaboration is essential to innovation because it allows us to combine diverse perspectives, skills and experiences to create something greater than the sum of its parts. It offers an opportunity to apply learnings from other areas to our problems. For the rest of this talk, I'll step through a few examples of the sorts of projects we have underway and discuss the sorts of flavours of collaborative projects that we're part of. On the right-hand side of the slide, I've flagged the different categories of collaboration. I'll touch on these during the rest of the presentation. Each plays a different role in the projects that we run as a geological survey. The first category is intergovernmental collaboration, and this is something that we've been doing for a long time. We primarily collaborate with Geoscience Australia and also the other state and territory geological surveys. These programs are either driven by us in the GSQ, they're a joint program where both parties are contributing equally, or they're very much driven by Geoscience Australia. It just depends on the scope of the work that we're doing in the program. So these are the ones, some of the ones that we have underway at the moment. Hopefully most people are familiar with them. You can see they're primarily geophysically driven projects, with the exception of the data-driven discoveries project, which was mentioned earlier. That's a program that is looking at hydrogen storage in the Ada Vale Basin alongside more traditional commodities such as gas. So that one's being led by Geoscience Australia because that's one of their priorities in this space. We don't have a strong impetus to work in that space in the minerals group, so we're supporting that program rather than driving it. I want to just highlight, in each category I'm going to highlight one project, and this one is one that I wanted to highlight in the government collaboration projects because I think it's a very unsexy project, but it's a really important project. This is, the AFGN is the Australian Fundamental Gravity Network project. what it involves is a network of places across Queensland where we know exactly what the gravity response of that part of the Earth is. And so those gravity stations allow us to tie all of our gravity surveys together so that we can not just use the data that we've acquired on our own tenement, but we can utilise all the historic gravity data that's been collected and tie it together so it models well together, it can be interpreted together. So this is really a fundamental backbone to gravity acquisition in Queensland. And this year we had Roger and Geoscience Australia, so Roger's part of the GSQ, and Geoscience Australia go out together and put in some new stations so that the contractors have a better way of tying their data together and making sure it's as usable as possible. So not very sexy. No one is probably ever going to use this data unless you're a gravity contractor, but it's a fundamental and very important part of the work that we do with Geoscience Australia. A second flavour of collaborative project that we've seen an expansion of in the GSQ are those primarily driven by collaborative partners. These partners could be researchers or industry experts, and this is a style of collaboration that is allowing us to expand the scope of projects being conducted by the GSQ. The alliance concept that Rick was talking about earlier today is what the future of this sort of work might look like. So at the moment we have a disparate set of projects with various research organisations, but maybe in the future expanding out into different parts of the value chain will be supported in a more systematic way. Our GSQ staff have varying levels of involvement in these projects, but the bulk of this work is actually being conducted by our collaborators. So I'm not trying to steal credit from them. I really want to acknowledge that there's a lot of work going on in this space that's funded by the GSQ, but driven by our research partners. I've cherry-picked one to have a bit more of a deep dive into to show you the sorts of really different projects that sit under this umbrella. So the neodymium isotopes traceability study is being conducted with colleagues from the University of Queensland and JCU, and it spans a range of disciplines from isotopic geochemists to hydrometallurgists to botanists, and what they're doing is building on the work of a previous program to advance the knowledge of rare earth processing. This project, in a nutshell, is a pilot study into characterising material from rare earth deposits to test whether recent advances in neodymium isotopic analysis means we'll be able to fingerprint ores produced, that is rare earth ores produced, so that instead of tracing a specific material throughout its life cycle, we can just analyse the neodymium content of it and know how it's been processed. So the teams are using neodymium isotope ratios from various materials, from primary ore to waste, plant material from phytomining experiments, trying to understand if there's a systematic way that neodymium isotopes are moving, so that the physical or chemical processes might be leading to partitioning of neodymium isotopes in materials that are produced differently. The first location for this project is Mary Kathleen Mine, which is at the bottom. And as the program evolves, other sites will be involved as well. I think we can all agree that this is a very long way from any of the projects that the GSQ has been involved in the pre-competitive data science, pre-competitive geoscience space. But in a world where consumers care how their materials have been produced and what the environmental and social impacts of that production are, this kind of work could play an important role in positioning Queensland's critical minerals as a highly desirable product of choice across the world. So much of the work that we do in collaboration with universities involves either students or early career researchers. These people are the future of our industry, and our projects benefit enormously from their hard work, because they do work tirelessly on these projects, and the insights that they generate. I've seen people looking at the posters during morning tea, and if you haven't had a chance, please go and look at them. There's some wonderful content out there. And I will remind you that there is also an opportunity to talk to the researchers in our extended lunch break and also vote for the project or the poster that you think is the best. The projects listed here don't do justice to the amount of work that the students and early career researchers contribute to our projects, so please take a look at the posters. Again, I've chosen one, and this is not exactly a student project, but it's an entire work program built on the results of a student project. So it really highlights the power of this sort of student research. So I'm sticking with the theme of isotopic characterization for this project. The Isotopes Undercover project being run at the GSQ involves data acquisition and characterization by isotope geochemistry from groundwater and ore samples across northern Queensland. This work is being done in partnership with leading national and international researchers and is helping to develop the new tools and data sets for the exploration industry to use. The key part that is the student involvement in this is that the program is largely led by experienced researchers, but fundamentally is built on results from a PhD student, Chris Prato from the University of Michigan. His early work in this space has really been the impetus to expand these programs out and generate this entire work program. So you can see the power of the innovation that student projects can have to shape our future. And I think involving students in our projects is a great benefit to us because it allows us to show students the challenges that we're facing and also make sure that we have talented people coming into the industry going forward. So my fourth category of project is joint projects. So these ones are where there's a really active involvement from the GSQ staff and our external collaborators. You can see we're back more in the traditional pre-competitive geoscience space because that's where the real strength of the staff that we have lies. Again, there's a huge amount of projects here, some of which we discussed throughout the rest of the day, but this kind of collaborative project allows us to bring together researchers and experts from both within and external to try and tackle some of these problems. Again, cherry picking one of these projects. This is actually one that I was personally involved in. So the seismic interpretation project has been running for a number of years now. It's come out of an acknowledgement that deep crustal seismic data acquisition is a very significant investment by government. This is not a cheap data set to acquire, and northern Queensland is crisscrossed by a network of this sort of data. Some of it has been interpreted and some of it hadn't been interpreted when this project started. As is so often the case, large-scale geophysics projects can find it hard to do that last 10%. You collect all the data, all of that's done, and then it requires an additional investment of effort and time to do the interpretation to really get the most out of these data sets. And for some of our seismic lines prior to this project, that hadn't been done. So this project involved Karen Connors from the University of Queensland working together with myself and Dominic Brown. So Karen is a petroleum background person with seismic experience. I'm a geophysicist in the potential fields magnetotelluric space, and Dominic is a hybrid geologist geophysicist. He has magnetotelluric knowledge. He's got isotope geochemistry knowledge as well. And so we brought together three quite different people to work on this project to generate the interpretations you're seeing here. So this is from phase 1 of the project. Phase 2 extended it up into northwest of Mount Isa. And then phase 3 is actually being done with a different research group to try and build on the knowledge that exists in northeast Queensland. So we're bringing together people from James Cook University to expand this work out into the Georgetown area. I believe Matt might be talking about this in a bit more detail later as well. Moving on to what I consider the fifth kind of collaboration we do. This is our grants programs. I'm going to touch upon this really, really briefly because Heather's got an entire talk about this later today, but I think it's important to acknowledge that the grants are, to our mind, maybe not to everyone's mind, a form of collaboration. We try and fund the most innovative, most useful, most groundbreaking research that we can in industry, and hope that the injection of our funding gets these different projects up off the ground where they might not otherwise have been successful. There are a range of grants programs. We've got the traditional CEI grants program, and just to make things difficult, we've got a new grants program, the CDP grants program, because who doesn't love a three-letter government acronym? That one's in the secondary prospectivity space and the gas grants. So Heather will be covering these later. And then the final kind of project that we do, again, still built on collaboration, but maybe less visibly so, is the GSQ projects. So I'm not going to go into any detail for any of these projects because these are deserve a lot more time than I can give them, and the GSQ staff are going to be presenting on these throughout the day. So I just wanted to flag that these projects are built on collaboration. We have university people involved in them. We've got other researchers involved in them. We're using industry materials to do some of these. So we really do rely on the collaboration across government and industry and research to get these sorts of projects up and running. I think, so that's a very whirlwind tour of all the sorts of projects that we're doing. So I think we can agree that it's quite a staggering number of projects going on. And if you want to know more about any of these, how do you find something about them? The best place to go is to our open data portal. To make things a little bit easier, we've got a couple of master links there for different funding initiatives where we've kind of aggregated all of the projects that sat under, for example, NEMI. You can look through the list of projects. There's high-level summary of what the project involved, and then a link to any data or reports associated with it. So this is trying to make it easier to navigate. QRIDP is not yet in data delivery phase, but as we enter that, another one of these catalogues will be generated for all the projects sitting under that funding arrangement. But you can also just search in a map view or through keywords. Like, you don't have to go to these. We're just trying to make different options available to make the data as accessible as possible. Before I get kicked off the stage, so I guess that's a lot of stuff. So what am I trying to say? I heard this in a presentation a while ago, and it's been bumping around in my head for a while. Innovation is not a sprint, and it's not a marathon. It's a relay race. We're all got a part to play in the journey towards finding critical minerals and generating the innovation we need to produce them and sell them to market. What we're trying to do in the projects that we're generating inside GSQ is play our part in that innovation, but also partner with all of the other people who have their parts to play and push the whole thing along. So that's why we do collaboration. That's why we do these sorts of projects, to be more than the sum of our parts. That's it.
Thanks very much, Janelle. And Janelle did flag she may run over time, and you've done a pretty good job of keeping to script, so thank you for that. Matthew Greenwood is the next presenter. Matt's the manager of regional compilations at the GSQ, and the title of his talk rather, is Regional Geoscience and Geophysical Programs. Over to you, Matt.
Awesome. Thank you very much, Evan. My name is Matthew Greenwood. I'm the manager of regional compilations at the GSQ. I'm going to be covering a range of regional geoscience programs conducted under the New Economy Minerals Initiative and the Queensland Resource Industry Development Plan. I'd like to acknowledge contributions for this presentation have come from a wide selection of my team and the broader GSQ. If you have any questions about any of these programs, please feel free to contact me, and I'll put you in touch with the officers from the GSQ that were involved in those. I'll start off with the Ainslie Mag survey, which keeps building on the open file geophysical potential field data in Queensland. At last count, there are more than 8 million line kilometres of open file airborne geophysical data available in Queensland, which is equivalent to 200 laps of the Earth or 5.5 times the distance the Apollo 11 mission travelled. So there's a massive amount of just airborne geophysical data available, as well as the combination of all the other data available in our portal. The Ainslie survey is a 100-metre mag survey to the north of Georgetown, 60-metre survey height, and about 120,000 line kilometres. As well as our traditional mag-rad data we're collecting on that survey, we also have wingtip magnetic gradiometry, which will be there. 3 crystal packs, which means you'll get much more resolution in our radiometrics. And also, Excalibur has the Ichorus gravimeter in that plane as well. So we should get some airborne gravity data in that area as well. Currently, survey flights are about 60% complete for that. We're looking for a completion in January of that survey, as long as weather holds out for us, which is a very big wish up, I guess, in Georgetown area. And the data will be released after final QA/QC early 2023. Once we complete that survey, hopefully the odd shape of the survey makes a bit more sense now, that it is wrapping around other surveys available in the area at 50-metre or 100-metre line spacing. Once we get that final data available and released, we'll then be looking going back, similar to what we did in Mount Isa, and merging up all the data to create quite a large merge at a high resolution across the Georgetown-Croydon area and extending down to the south and east as well. As part of the Queensland Resource Industry Development Plan, we're also going to continue with our collaboration with Geoscience Australia on the AusAEM 20-kilometre line-spaced AEM survey. We have a proposal for continuation of that survey, lines out towards the coast of the AusAEM-1 data collected in 2017-2018, as well as the blue box here, which is a regional 2-kilometre line-spaced AEM to infill areas in the AusAEM-1 that had significant conductors in the basement at cover depths that we were able to see. The tenders for those surveys are currently out with Geoscience Australia, and we should have the survey started in April through June of next year for both of those, the AusAEM and the regional AEM survey. Continuing the geophysics space, we're going to conduct a new airborne gravity gradiometry survey in the Georgetown area as well. Similar specifications to the Kenobi survey, so a 1-kilometre line spacing survey to improve the 3 to 4 space ground station surveys in the areas both around the outcropping and covered Georgetown terrain. Again, that tender is out to market right now with Geoscience Australia, and we expect responses back next month, and the survey starting up through April through June 2024. The combination of those 3 surveys, the Ainslie Mag survey, the AEM survey, the regional AEM survey, the AusAEM survey, and the gravity gradiometry survey, means we're going to have a lot more new geophysical data available in that Georgetown-Croydon area that will enable new geological mapping and new geological projects in that area, and I'll touch on that again a bit shortly. Janelle also mentioned the AFGN data updates that Roger and Geoscience Australia were able to conduct. Through that survey, the AFGN provides a set of known points with recorded absolute gravity values to enable those relative gravity surveys to be tied to a consistent datum and data from different surveys to be merged and incorporated together. The AFGN sites are maintained by the GSQ and Geoscience Australia, but over time, as sites are destroyed, we need to be replacing those surveys. So this trip in May 2023 visited 33 stations. 15 were found to be in good condition and they were re-recorded at some points. 18 of those sites were found to be destroyed or lost. 12 new sites were deployed and all measured were with the A10 absolute gravimeter. So you can see our set of new points that were collected as part of that survey, and they've been available in the AFGN portal through Geoscience Australia. So those new AFGN sites can be used to tie in those relative gravity surveys across the area. Janelle also stole my thunder on this program, talking about seismic interpretation in North Queensland. This is looking to create an integrated interpretation of those deep crustal seismic surveys across the state. The Phase 1 report has been released, covering a majority of the surveys in northwest Queensland. Phase 2, we continue that work into further up west, into the northwest. That report is with publishing, ready to be produced shortly. And Phase 3, as Janelle said, is moving towards the eastern coast of Queensland to incorporate some of those lines out towards Georgetown and then Charters Towers. That is with James Cook University, utilising their skills and experience in that part of the state. We're also planning to conduct a deep seismic survey in the northern Queensland. We'll be talking with Geoscience Australia into the new year about the plans for that survey. And while I'm on the topic of seismic as well, Ao Shang, our new embedded researcher, a postdoc researcher at the University of Technology in Queensland, Queensland University of Technology, QUT, sorry, has a poster outside where she's looking at using the AusPass passive seismic data to improve understanding of regional crustal evolution and crustal geology using some new techniques in that passive seismic modelling. So please check that out as well if you're interested in some more seismic information across the state. The CCA magnetotelluric survey is building on a framework of sites across the eastern sub-province of Mount Isa Inlier to better understand the Carpentaria conductivity anomaly that we've seen in both the Cloncurry and Cloncurry Extension MT surveys, as well as the CF2-3 MT surveys, which were conducted along those seismic profiles. That work is ongoing. The survey, there are sites currently out and deployed right now. We've collected about 185 of those 320 stations, and that survey will be completed into 2024, and the data made available once the final QA/QC has been done. But the green labelled sites there have been collected. The white sites are still to be deployed. So we're continuing on with that program of collecting new MT data to enable an understanding of the crustal architecture and the connectivity structure of the mid to lower crust. Continuing on MT, we're also continuing to work with Geoscience Australia on the AusLAMP coverage as well. So it's a continental-wide coverage of MT undertaken by Geoscience Australia, but supported both financially and with fieldwork from the GSQ. The coverage of much of northern Queensland is completed, and we're continuing that coverage across to the east as well. Inversion and modelling that data is available from Geoscience Australia. So moving from the geophysical area where I'm far more familiar and into the geoscience programs we've done at a regional scale, I'm going to start with the North East Queensland Solid Geology Program. This is a program being conducted by Bob Bultitude and Josh Spence. The work here is focused on improving the solid geology interpretation in the Georgetown-Croydon region, utilising both the geophysics that we're collecting over the area, the new MAG surveys, new gravity and new AEM data, and updated geochronology and geochemistry work. So to date, there's been 3 weeks of field work, getting a bunch of samples from undifferentiated Silurian Permian igneous units for dating and geochemistry and geochronology, and interpretation of some of those samples and those drilled samples that were collected as exploration program and the compilation of that data. Once we get that new geophysical data available, there'll be a follow-up work doing some interpretation on that geophysics, as well as follow-up mapping to understand differences between our geological understanding and the geophysical interpretation of those areas, and publishing some new records about the solid geology in the Georgetown area. The Peralkali Magmatic Systems Survey, systems work, is a program led by Dave Purdy. The program is nearing completion, with all key units identified and inventory now complete and now sampled for geochemistry. The work has resulted in mapping improvements across the eastern coast and a greatly expanded geochemistry database. Detailed descriptions of several of these units and petrogenetic interpretations of some of these units are now available and being published around the Nebo area. In one area where there was poor surface exposure, we have conducted a UAV magnetic survey, which will be released shortly as well to enable understanding of the extension of some of these units undercover. And we're still awaiting some isotopic data that we have and some more sampling in southeast Queensland to continue. But overall, when we look at the geochemistry collected in the project, it does seem like the peralkaline azurine rhyolite domes in the Peaks Range are a bit of a unicorn in the area. They are unique in their peralkalinity and their high field strength element components. And they also appear to have a different vocalic forms and different petrogenetic history to most other units in the area. The questions here are why? Isotopic data hopefully will help us understand this better. And there are some outliers from other units that approach the peak range in terms of their composition. But for some elements, and these samples might be worth following up with more detailed study. The big question that I think Dave is looking at now is, are we looking at different, were these units all central volcanoes? What can the volcanology and the distribution of the different lithologies tell us more about the emplacement of some of these rocks? Another new program is our halloysite nanotubes program, which is led by Siraj and Dave again. Geoscientists from the GSQ have been collecting samples from clay pits across Queensland, looking at occurrences of halloysite and naturally occurring tubular clay in the kaolin group, which has numerous high-value applications in nano containers, controlled drug release services, as well as chemical scrubbing for carbon dioxide capture, as well as hydrogen storage. We've completed a reconnaissance survey in Queensland to identify the presence of halloysite from kaolin, and about 40 sites have been sampled so far. And Dave has termed this the Great Clay Belt, which is not yet in the stratigraphic unit relationship yet, but maybe it will be soon, Dave. As just a bit of an understanding of some of the sites there's some quite spectacular geologic expressions in some of these clay sites. This is a site near Kingaroy, and there's further analysis of the work still to come. But initial screening with the HiLogger and XRD are looking positive for some sites. This site that I showed before looks positive for halloysite potential, and detailed characteristics of these samples will be done in collaboration with CSIRO. Future work on more sampling of field sites and follow-up prospective samples with quantitative assessments of the mineralogy and the extraction of viability and applications to follow. Another program being conducted by Don Brown is looking at the regional prospectivity, so capitalising on areas where we have a vast amount of information. This is focused starting on the Eastern Succession in Mount Isa, compilation of the open file data both collected by the GSQ and through exploration reports, updation of the geological framework and creation of new products, including a one-dimensional depth basement probabilistic model produced from the MT data with CSIRO, and Janelle and Dom worked on that together as well. Update of new geochemistry in the area, and a solid geology update which is being undertaken right now, and that's a work in progress at the bottom of an updated solid geology interpretation of this area. One last program to talk about is a collaborative program that I'm quite heavily involved in between the GSQ, SMI, and a startup in Brisbane called Euclidean. This is looking to build a 3D digital twin of the geoscience data with initial focus on the deposit atlases, which we'll talk about later today, and the regional data. It's bringing together all the data we have in a certain area across multiple scales into a data discovery tool. We've had a proof of concept. We've embedded the three-dimensional data from this product into the two-dimensional data from GeoResGlobe. And we're now developing a standalone application that will enable users to interrogate this data in a 3D space. And I have a bit of a video to step through. So this is starting from the whole of the state, looking at the geological model of Queensland, zooming through. We can bring on the AEM, so you can see we're looking down through the earth as well as just on a planar surface. We have the MT inversion there we're looking at now, so the MT inversion under Cloncurry, and then we have I apologise for my zooming, I struggle with this sometimes, the pit design of Ernest Henry that sits below that MT anomaly. As we go further into Ernest Henry, you can zoom into particular high-logged core where we can see the imagery of that high-logged core in the same space. So this is working across the multiple scales that we work at, from regional scale down to imagery of core. And then as I go further, we're going to come to an XRF scan of one of those pieces of core. So micron-style pixels, where we have XRT tomography of core in the same model as we had the entire statewide data set. So this is a work in progress that we're continuing to develop and bring more data into, but the initial standalone app hopefully released in 2024 through that program. Thank you very much for listening.
Thanks very much, Matt. If you do have questions for Matt or any other presenters, please take the time to speak with them at the break times, but we'll go on to the next presenter, which is Joseph Tang from the Geological Survey. And Joe will be presenting Hydrogeochemistry, a greenfield exploration tool in northwest Queensland. Welcome, Joe.
Thank you very much. Before I begin, I'd just like to acknowledge our collaborators. It's CSIRO, Queensland University of Technology, James Cook University, and Junita College. And they are really integral to have this success for this project itself. Sorry. Technology. Okay. For this talk, I'll sort of introduce basically what geochemistry is in the exploration world. That's because in the interest of time, I won't go into the detail, but would highlight enough information so that you could understand what this program is about. I have sort of posted links to reports and talks that I have given in the past, and you could download this. It's at the end of this presentation. You could download the whole sort of publication or talks and sort of view in your own time. I will also talk about metal isotopes, which is a really additional sort of strength in hydrogeochemistry. It's a new technique that complements hydrogeochemistry. Then I'll move on to the second part of this talk to look at the 2023 sort of hydrogeochemical program itself. I'll put a lot of emphasis on the Georgetown project. I'll explain why, because it's rather unique. Because this is an ongoing project, I have not received all the geochemical results from the labs, and so I can't talk about the results itself. But I'm going to analyze what's available over that area, the geoscience behind that, and understand and build up the geochemical systematics in that area, as well as in the Northwest Queensland. Well, you heard this phrase before, that if you want to hunt for elephant, you got to look at the right elephant country to hunt. We heard a lot about critical minerals today, and I'll sort of highlight, if you want to find critical metals in Northwest Queensland, you got to find the right ground, and that's exactly what this talk would be about. Hopefully, the fundamentals that I've created would give enough information to answer those three questions in exploration: the what, the where, and the how in mineral exploration itself. Water bores are generally probes to the subterranean. Basically, it samples chemistry which conventional geochemistry, when I mention conventional geochemistry, I'm talking about salt, swim sediments, and rock chips, etc., cannot reach. Basically, the depth of sampling from the boreholes depends on the depth of borehole. It goes from tens to hundreds of meters, and therefore provide a really good window to the underlying geology and geochemistry. Well, the concept behind is very simple. When pore water interacts with rock, it reaches a chemical equilibrium. Basically, if you sample this water, the pore water from the formation itself, it will give you a really good chemical indications of the lithology, the chemistry of the rocks, the alterations, and the mineralization. And when you combine these together, it gives you a good prospectivity mapping of what's underneath. Work that we have done with CSIRO, as well as research by CSIRO and by MIM, has found that sampling boreholes spaced between 3 to 5 kilometers would provide a really good coverage of geology underground, sort of subterranean geochemistry and geology itself. Geochemistry, or hydrogeochemistry, is very different from conventional geochemistry. Firstly, you do not create a new sample site. It's an opportunistic sampling, because you only pick sites that's already available. There's borehole, drill hole, etc. that's there. And so it takes a lot of planning, a pre-planning to pick which hole, where you sample, so that you get enough depth, enough coverage, and enough sort of information over an area to find out what's in the underlying geology itself. Hydrogeochemistry is also very different from conventional geochemistry. Firstly, it is not a static commodity. It's a static sort of state. It varies over time, over seasons, and over the years as well. And it's affected by factors like evapotranspiration, water recharge, water discharge, water mixing, and physiochemical properties like temperature, pressure, acidity, etc. The other thing that is different is that it has no boundary. The sort of extension, or the influence from a borehole changes with different season and with different hydrology itself. Oops. Well, what do we sample when we talk about hydrogeochemistry? Basically, we are targeting formation water. In this case, trying to sort of get the mouse here. In this case, it doesn't. Basically, what we are looking at is a formation water. When you pump from a well, you basically depress the water level and create a drawdown cone itself. The drawdown cone around the water would create a negative pressure that eventually draws the water from formation upward into a sort of updraft. And when you pump and sample from the bore, you're actually sampling both the formation water as well as the sort of semi-confined water. And so it's a really mixed water chemistry of both formation and the semi-confined water, and making it rather more difficult to interpret than normal chemistry itself. In terms of field procedure, it's very simple. It's 5 different steps. Firstly, you need a pre-planning, and then you locate the bore. The next step is that you actually measure when you reach that, basically you measure the locations and water table itself. And the next thing is sampling. When you talk about sampling, the best sample is taken directly from the bore or directly outlet from the bore. And this may mean that you've got to climb up 5 meters or 3 meters up a water tank and collect the sample there. Once the water is collected, you have to do the physical test within minutes from collection to look at the temperature, the redox state, the conductivities, and the pH itself. And then, for every borehole, there are 4 different samples for basic chemistry. 2 unfiltered ones for gold and alkalinity, and 2 filtered ones for cations and anions. If you do additional testing, like isotopes, you would have to take additional samples for copper and zinc isotope itself. Well, all the samples that we collected are sent to specialized lab. For the best metal, we send it to CSIRO in Perth, where they analyze for 66 elements, including another additional 8 elements for salts. And this brings together almost 70 different parameters in the geochemistry. For copper and zinc isotope, we send it to Junita College in USA for testing. And for the lead isotope, we send it to QUT, where Professor Bas Campbell analyzed all the water for the different lead isotopes. The metal content in water is very, very low. You're talking about parts per billion to parts per trillion. And therefore, it is very challenging to sort of interpret the data, because most chemistry is just marginally above detection limit or the best level itself. There are 2 ways of interpreting the data. One is by single element analysis, where you just look at single elements, try and sort of determine where the anomaly is. And that could be challenging because, like I said, some of the anomaly is really very low compared to the background. Second one is multi-element indices. Basically, what we meant by multi-element indices is to combine a group of metal together and use that as a proxy for different mineralization style. For example, if you look down the second line, we could look at copper, zinc, platinum, and silver as a proxy for VMS type deposits. And when you combine the different elements, you will sort of get a good idea of what sort of mineralization it is. This indices varies from place to place because this has to be trained to the local conditions. And therefore, part of this talk will be to talk about how these indices is established in the Mount Isa region, or the sort of Joshan region. This is the results from the earlier study that we've done in the eastern Mount Isa region. From this work, we have identified 13 areas of mineral interest. And this report has been released, and you can download the whole report itself. The same data can be, has been tested for lead isotopes, where QUT has tested it, and we superimpose this data over the work done by Graham Carr, by CSIRO, to identify the IOCG, or the sort of Proterozoic type deposits. And it identified 4 additional areas. The one near Kelowna, which is the northeastern one, is one of the most sort of prospective area for copper or copper gold sort of deposits. Then we found other areas like L. Lewis, Kennington, and Tullabug area. And all of these are being chased up by explorers, I think, at the moment. Another method that we've done after this project is concluded is the copper isotopes, where we work with JCU and Junita College, where we look at the copper isotope in water. Basically, when copper sulfides weathers, it breaks down. The weathered material is enriched in the heavy copper, the copper 65. And if you get a good way of determining the ratio of copper 65 to the common copper, copper 63, you will find that the proximity to a mineralization. In other words, you could telescope into where the mineralization up is. Therefore, groundwater on itself can be used as an exploration tool, or you can use it in combination with other things like isotopes to look at a mineralization itself. Next, we move on to what has been achieved in 2023. Before we start this hydrogeochemical program, we did an inventory of what has been done. Basically, there are three sort of package of work that's been done. The biggest of which we have completed with our CSIRO is the 302 samples that we collected. Oh, sorry, I forgot to mention QT and South 32 as well, that assists in this. And that package of work. The second package of work is where we work with JCU in the L. Lewis area. And the third package of work is the work undertaken by Explorer, by Rio Tinto and Moho Resources itself. When we look at the data that's compiled, we can see there's a lot of data gap. That's where GSQ comes in this year to fill up those data gaps. So we have a continuous undercover chemistry from McKinley down in the southern part up towards to Gregory. Also, we start another new program in the Georgetown area. When I mention Georgetown area, the brown color is Croydon and the sort of light brown color is Ettridge. We combine them to, in a colloquial term, Georgetown area. Because Georgetown area is a new area, we don't know much about the geology itself, so we did both undercover and within the outcropping area. What tells a million stories, so I won't have time to go into that, but that's the kind of work that we photos that we take as part of this field work. Well, the question we have to ask is Georgetown special? That's a question that I think most explorers would ask before you get into an area. Well, what I've done is this: I pull out the baseline chemistry from catchment chemistry over the Georgetown area and normalize it to the Australian sort of national average. I'll talk about this normalization factor later on. But what it shows is if you look at the Georgetown area, it's really enriched in one thing: rare earth. The colors in green are the rare earth. The second thing is the high field strength element: tin, tungsten, niobium, tantalum. And the other things that is enriched are uranium, thorium, gold, silver, gallium, and the LIL, the light lithophile itself. When you sort of look at this together, what does it tell you? Critical metals, that's exactly what it is. And so Georgetown area, it's really potential for critical metals. It's low in sulfur, which means that it has a different genesis compared to the other areas, that it's driven by light lithophile elements. We also normalize the chemistry from Georgetown with Mount Isa region. The reason for this is we are doing work in both areas, and whether to treat them as one population or multiple population. And by looking at that, you could see quite clearly it's very different. The Georgetown area is enriched in the high field strength element, uranium, thorium, and it's also high in gold. Whereas the Mount Isa area is enriched in copper and sulfur. So it has a very different genesis. And so we can't treat them as one population, and this has to be split up. Next thing that I have done is to look at the mineral occurrence data. This is a database where, that runs for more than 20 years, and finishes, I think, in 2017, where every location in the Northwest has been mapped by recording the mineralogy and the location of that. And I plotted the distributions of occurrences in the Georgetown area. It's massive. What I've done is this: I translate those mineralogy into chemistry, and then by turning into chemistry, I can process those data. And this is the results that I've plotted on. It shows really clearly that there's two different mineralogical provinces in this area. The eastern area, which we call Georgetown East, is dominated by tin, which is in orange, and tungsten in yellow, whereas the western part is dominated by gold in red and copper that's in brown itself. So there is a very different genesis of metal in this area. The Croydon province is really interesting. The same Esmeralda granite has a gold-rich northern part and a tin-rich southern part. It's something that really triggers interest in GSQ that we will have to go back and re-examine this thing itself. This is just another sort of summary of the mineral occurrences when we translate from mineralogy into chemistry. And you could see the very differences, different, sort of mineral association in the eastern part compared to the western part itself. Next, I also pull in the baseline chemistry, the catchment chemistry, where I process all the 66 elements by normalizing it against the national sort of average. When we talk about sort of a normalized data, basically we get the differences of that catchment chemistry to the national or to the reference material and normalize it to that reference sort of chemistry. Anything more than 0 means it's enriched. Anything less than 0, it's depleted. Having done that, you could see that we normalized the eastern part of Georgetown against the western part of Georgetown. These two, the one on top is the eastern Georgetown, and the one at the bottom is the western Georgetown. Same enrichment factor on the y-axis, and same arrangement of elements on the x-axis. What it shows is very clear, very different skyline. In other words, the eastern Georgetown is enriched in the lithophilic or the oxyphilic minerals, tin, tungsten, niobium, tantalum, uranium, thorium, etc. And the western Georgetown is enriched in gold. One thing that's really interesting is this. As mentioned before, is this. Lead is always, sort of enriched, in the outside Georgetown, Mount Isa region. And there's something I've mentioned many times, and it's something that probably explorers should be interested about that. What I've done is also to turn those immunochemistry into correlation coefficient. It's a long process. And you could see that it's a very different, chemical sort of, packaging between the east and the west itself. When we bring together both the MinOc data and the background data, these are the different associations that's been established. The chemical association that's established for eastern Mount Isa against western Mount Isa. What it shows, the top 3 in the eastern Mount Isa, the ones in bold, are the major ones. The black bold ones are factors developed using the MinOc data, and the gray ones are based on factors developed using the baseline chemistry. So what it shows here is this. You got very, very different chemistry itself, very different mineral sort of formation between the two areas. Therefore, you have to treat this Georgetown area as 2 different entities when you start exploring. Well, next we move on to work accomplishment in 2023. What have we done? That's a lot. What I've shown here is the same picture, except I've superimposed the age of different granites here, although I think it's a bit early days at this stage. I'm not going to sort of predict, but it really has different granites. I don't know whether it's genetically sort of responsible for mineralization, but it really is an interesting sort of proposition there. What we've done is this. We collect 293 boreholes in this program, of which 160 comes from this Georgetown area. And we've sent all of this to CSIRO. It's been analyzed at the moment. We also sent 78 samples for copper and zinc isotopes to Junata Collection USA for analysis. It's in the lab now. And after we analyze the samples for bulk metals, samples that has more than 1 parts per billion will be sent to QT for the lead isotopic analysis. Well, lastly, oops. What's next for 2024? I know every one of you are probably sort of waiting in anticipation and curiosity. What's coming? Well, this is what we have in plan. I'm hoping to get all the chemistry, the the isotopic chemistry for zinc and copper, as well as trace elements back by the first quarter, or hopefully first quarter rather than second quarter. I'm hoping to get the copper isotope data back by the second quarter of next year. And once we get the data, we can start processing this data and produce a report, which we hope to release in either the 3rd or the 4th quarter of next year. Thank you very much. Yeah. Lastly, I would like to thank all the field staff, the field teams and the support teams. And I also posted all the work that has been done with the links there that you could download the full reports or the full talks, available online. Thank you.
Thanks very much, Joe. Our final presenter for this session from the Geological Survey is Roger Cant. Roger has just given me an updated title, which I'll remember, Petrophysical Acquisition in Queensland. Welcome, Roger.
Thank you, Evan. My first encounter with petrophysical acquisition was when I joined the GSQ as a newly graduated geoscientist within the geophysics team. I'd spend 4 days a week trawling through company reports, finding and cataloguing recently acquired geophysical surveys in Queensland. On the 5th day, though, it was spent out at the Exploration Data Centre in a small corner of the core viewing area with a piece of drill core in one hand and a KT9 in the other, beeping away as I measured magnetic susceptibility for some project unknown to me. Stationed next to me was my trusty 80-litre green bin filled to the brim with water and a set of scales perched precariously above it with a hook and net attachment, ready to submerge and weigh my piece of core for density. After 6 months of this, the geos must have finally felt like they'd seen enough core for their project, and I was relieved and hopeful that I'd never have to balance and weigh drill core in that bucket of water ever again. And apart from a few days in 2016, my time acquiring petrophysics has been all but a distant memory. Whatever happened to the many rather ad hoc measurements of mag sus I made and densities that I calculated? Were they ever used for anything? Hopefully, they were used for some quick and dirty forward modelling by the project team. Or maybe they just live locked away in Appendix A in some zipped file somewhere in the GSQ Open Data Portal, which I can't find. I don't know, I've never thought to look for them again. So, when the Mineral Systems team floated the idea of acquiring petrophysical measurements on top of the extensive data that they are already collecting as part of the GSQ reference collection of mineral systems, and there'll be more of that spoken after lunch, we knew that we needed to acquire the data in a far more sophisticated, standardized, and accessible way than previously done before. Plus, we didn't have any graduates willing to go out to Silmia and spend their time zapping core and getting their hands wet. The dream, of course, would be to take a core tray, fresh from the high logger, and send it into a similarly automated machine to make continuous measurements for any sort of suite of petrophysical analysis, and then pass it on to the geologists for their sampling. I'll not surprise any of you, though, that such a tool does not exist. So we looked around at what tools were available in the petrophysics space, and were fortunate enough to be able to borrow this instead. The Mobile Petrophysical Laboratory, or the MPL. The MPL project is led by a team at CSIRO, together with the University of Melbourne, AuScope, and the National Research Infrastructure for Australia initiative. What they've done is essentially installed a Geotech multi-sensor core logger into the shipping container, shown above, and created a mobile lab and offer it to users around Australia who are wanting to collect petrophysical data. Now, I've taken these words straight from the CSIRO's MPL page, but in essence, the program is being run to promote the acquisition and use of petrophysical data within the mineral exploration industry to improve the success of exploration undercover. Petrophysics already plays a huge part in the petroleum industry, but is largely underutilised by minerals explorers, aside from a few magnetic susceptibility and, of course, density measurements made here and there. Through this project, GSQ is committed to providing industry and research bodies with access to more petrophysical data from mineral systems in a standardised format. We're also interested in understanding how we can scale up and use petrophysical data in new and innovative ways in our own regional work, as well as how it scales down and can be in use in conjunction with other disciplines. All right, what's in the box? So here's a schematic of the MSCL, as found in the mobile petrophysics lab. Starting on the right there, you've got the beating heart of the tool, the pusher. And a row of core is unloaded from a core tray and placed onto a little plastic boat, about 1.5 meters long, which is then pushed through the logger. First off, it hits the spectral density tool, which hosts a small cesium gamma source, and that's used to determine your density. No more water required. Next up is the acoustic velocity tool, which is shown here mounted vertically. However, in the MPL, it's actually mounted horizontally. There are then two magnetic susceptibility tools, a point sensor and the loop sensor, and between those two is the handheld XRF that's mounted there, and the operation is controlled by Geotech's login software. Next, the non-contact electrical resistivity tool does runs a quick inductive current over it to measure the resistivity. And finally, the natural gamma tool, which measures your potassium, uranium, and thorium. After the core has been logged, it's spit out the other end and removed from the left-hand side and replaced back in the core tray, ready for the next section to be loaded on to the right-hand side, and so onwards it goes. All right, here's some photos from inside the container. On the right, you can see 5 core trays there, ready to be logged for the day. The production rate will vary depending on the chosen sampling interval, what sort of condition the core is in, and how long the sensors are set up to measure. So currently we've got the XRF that takes the longest. It takes a minute because we use a 3-beam mode. Other tools that we usually set the natural gamma for 20 seconds, but other tools can be done, required measurements in less than 5 seconds. As the core is pushed through the logger, the numbers are plotted in real time on a graph there on the left-hand side, so the operator can notice if there's any really skew measurements happening and go and investigate. All right, so here's a typical section that's been manually removed from the core tray and placed into the boat that's going to be pushed through the logger. Each section is photographed using a camera conveniently mounted to the ceiling of the MPL. Before the core is scanned, the operator is required to input where any measurement skips are to be made. The MSEL can only sample competent length of core, and it has to be you want it to be at least 10 centimeters long. It's unable to log core that is crumbled, that it's highly fractured, or across breaks. To date, we've opted for 5 centimeter sampling, an interval of 5 centimeters, regardless of whether we're scanning the host rock or alteration. Note that we can't sample quarter core either, which does limit the amount of data that we're going to be collecting in many zones of interest. So for this section, out of the possible 17 measurements along a 90 centimeter runner core, we can only make 10 of those measurements due, of course, to those breaks across the core. And here's why we can't do that, why we can't measure across those breaks. You've got the spectral density tool, which uses volume to calculate the density of your sample. So if there's a fracture between those two pieces of core, it's going to be missing volume, and it won't allow the gamma, and it'll allow the gamma detector to pick up more counts, which is going to result in your density different to the actual value. The P-wave sensor next to it also needs a competent piece of core to allow good coupling with the core to transmit and receive the signal produced to be able to measure velocities. Also, because the horizontal arms move in and out to hold the core in place, if the core is fractured, there's a possibility that the core may be moved within the boat, which is going to disrupt your spatial logging across for the rest of the tool measurements. And finally, you've also got the XRF there, and you risk firing an air shot if it's not made in proper contact with the core. So what are we logging? Previous use of the MSEL saw logging of entire drill holes at 2 centimetre intervals as part of the Stavely project down in Victoria. I've got some of the data up there on the right from a paper by Phil from the GSV. While it looks fantastic, we simply don't have the time required, even at the course of 5 centimetre sampling we're doing, to do such a thing. Plus, we are limited by the quality of the core we're logging. Whereas the Stavely project was logging fresh drill core, much of the stuff we're doing is more than 20 years old, and so the core is so degraded that we just can't scan anything from some entire trays. We've instead opted for a breadth of data collection in line with the reference collected sampling across a range of different mineral systems in Queensland, which will allow people to start looking at using petrophysical properties in conjunction with geochemical analyses being done, looking at alteration zones. Rather than simply just defining rock property values for types of lithology, we want to investigate these alteration and how some of these measurements may differ throughout the mineralised body. Similar to how oil will increase your electrical resistivity, we want to use data we acquire to see what effect the presence of alteration may have to the petrophysical properties within a deposit. As of this week, we've completed logging on 20 holes. We haven't yet begun processing the data to date, and we expect that to start happening next month. As it passes through the QA/QC required, data will then become live in the Auscope portal under the boreholes MSCL layer. You can currently get data from Stavely there at the moment, and I believe South Australia will also be uploading some of the data that they've acquired using the MSCL as well. We'll also be releasing a compilation of the data through the GSQ Open Data Portal as well. So in summary, it's been a great learning experience for all of us involved with the MPL project. It certainly took us a good 6 weeks to get the thing working in a flow and how to best operate it. I haven't even mentioned all of the daily, weekly and monthly calibrations that are being done as part of the scanning process. There's still a place for using petrophysics for traditional lithology constraints and development to be made in that space as well. However, we'd like to see more petrophysics used in conjunction with geochemistry, investigating these alteration zones. And I'd like to acknowledge some of the work that Jim Austin and his team around his integrated petrophysics workflow have done and he's championed in the past. And finally, we're going to need and require a lot more petrophysical data and larger data sets to be able to continue to test and develop and answer new questions around how we can use petrophysical data to benefit the minerals industry. And so I'd just like to show off the team here, and I'd like to thank especially Shane Mule and Cam Adams on the right there, as well as Chris Hansen and his crack team out at the Exploration Data Centre who make it all possible, the Mineral System for feeding us core, and of course to our star geologist in charge of our operations, Angie Risk. Thank you all very much.
We're a little ahead of time. Are there any questions for Roger? No? Excellent. Okay, please join with me in thanking Roger and all the presenters from session 2. Shortly we'll break for lunch, but as I mentioned earlier, we do have an extended lunch break today, so please take the time to have something to eat, but also please go and check out the posters. We're going to have some buckets just out near the registration tables where we invite everyone to vote on their best poster. We want to celebrate the research that's being undertaken and award some prizes to the top poster authors. So enjoy lunch, have a look at the posters, and we'll reconvene at 1:50. Thanks very much.